All right. So in the previous probability distribution, we looked at the sum, the probability distribution of the sum of two die, right? In that case, the random variable, the one single variable that we're interested in on this probability distribution is the sum of the two die, right? So that's one example of a random variable. It is the thing in here, the thing that you are finding the probabilities of, right? The one variable, right? But it doesn't have to be sum. It could be something else. For instance, in other games, you might be interested in the probability distribution of the greater of two die, right? And so here we have another probability distribution where instead of sum and looking for the probabilities of those sums, we have which is the greater number and the probability of that number being the greater number, right? So here I've just rewritten what I've written on the previous page, except nice and neatly, right? And one thing I want you to notice is this. If you add up all of these probabilities, they add up to 1. And that's good because this shows me that you have covered the entire span of all the different outcomes as well as the different probabilities. So there's no part of this sample space that has been untouched, right? You've touched all of it. And here we see once again that as the sums go up, 7 will be the highest probability roll. It's the highest probability combination. And it starts going down after 7, right? And 2 and 1, it's perfectly symmetrical, so that these sides are just the same. 7 is sort of the pivot point, the mirror point. Now, if we're looking at, okay, we roll some die, and we're looking at what is the probability that the greatest number there out of the two is 1, right? Well, there's only one case of that, right? So when it's 1 and 1, the greater number, greater than or equal to, I guess, is 1, right? And so that's 1 out of 36. But notice that this doesn't go up and then down, because here, what's the probability that when you roll the die, that the greatest number there will be 2, right? Well, that's only going to happen in the case of 1 and 2, 2 and 1, and 2 and 2. So that's 3 out of 36, right? But let's skip down to 6. 6 is the highest number. So it's going to be the greatest number the vast majority of the time. For all of the combinations that are like 6 and 1, 6 and 2, 6 and 3, 6 and 4, right? As well as 1 and 6, 1 and 6, 2 and 6, 3 and 6, right? And so 6 is frequently the highest number. But we don't count 6 and 6 twice, which is why it's 11 out of 36, right? But even so, if you add all of these probabilities up, you have a total of 1. And this shows me we've covered the entire space. So these are examples of probability distributions of two different random variables. One is the random variable of sum, and the other is the random variable of greater number, right? And we could have a random variable like which is the product, right? So the two numbers multiplied together. We could have all sorts of different random variables that we're interested in. But that is the thing upon which the probability distribution is being decided, right? So that's the thing you want to find the probabilities of. Okay, so now we know random variables, we know probability distribution. What is expected value? Well, here's the thing. Once you have a probability distribution like this, so this is that the rolling two die, and what's the probability of the sums, right? So here, once you have this probability distribution of the sums, so that's our random variable, and we often call our random variable big X, right? We could also call it big I or big M or big Y, right? But we call it some big variable letter, sorry. It would be really handy to know the mean of this probability distribution, right? Because every distribution has a mean, right? And so it would be nice to know what the mean of this distribution is. And that's often called the expected value. That's the mean of the probability distribution, or the mean of the sampling distribution. The reason it's called the expected value is this. You know, over time, if you keep rolling two die, over and over again, right? These probabilities should emerge, right? The law of large numbers. So over 10 million rolls of two die, right? We should see the frequencies corresponding to these probabilities. It would be nice to know what we should expect, even without rolling two die, 10 million times, right? It'd be nice to know what the mean might be. On average, what should it be? So in order to find expected value, what we're really doing here is what we think of as a weighted average, right? Because this 2 is not quite as frequent as this 7, right? So this 2 shouldn't count as much as this 7. And this 12, although it's a bigger number, it shouldn't count as much as 7 because it's only going to happen a small portion of the time. So what we're really doing is what we're going to do is not only take the sum and somehow put it into our estimate, but we're going to weight it by how likely it is, right? So if it's very unlikely, it only contributes a little bit. But if it's very, very likely, right, then it contributes a lot, right, to the expected value. And once again, if it's very unlikely, it only contributes a little bit, right? And so out of those contributions, you should be able to see, what is the expected value over time? What is going to be the most likely value of this random variable? Okay. So in order to find expected value, you'll often see it notated like this: the expected value of x, this random variable. Also, another notation for this is mu sub big X. The reason why we think of it as a mu is that probability distributions are theoretical distributions. And remember, theoretical distributions are more like populations than they are like samples, right? So, but it's mu sub big X. It's not just mu. If it was just mu, that would be the population. But when you see mu sub big X, this means this is the expected value. Okay. This can be easily found by taking the sum from I, right? I equals 1, of whatever your x's are, right? So, so in this case, this is my x, right? Because sum is my random variable, times how likely it is, right? And we need to do this for however many x's we have, right? And so number of values, right? Something like that. All right, so here what we see is that if x contributes a lot, right, because the probability is very high, then this is going to be a bigger number. If x only contributes a little bit, its value is going to be a little bit diminished, right? And so when we add all of those up, we sort of hear the chorus of like who is the loudest, right? Like, and that's our expected value. So some people contribute a lot, some people contribute a little bit. When we add all of them up, what we find is sort of the true story. All right, so in order to find this, I find it helpful to use Excel. So if you want to download the available Excel file, I've put in all the sums as well as the probabilities. And if you look, I've just put in 1 over 36, but Excel will put it in decimal form for you. And what we want to do is, you want to think of this multiplied together as the contribution to the mean. How much is it contributing to the expected value, right? And so in order to do that, we would take this x and multiply it by the probability of that x. And so this 2 contributes a little bit. But let's copy this up to 7. But this 7 contributes quite a bit, right? So it's much bigger than this 2. And then it goes down again where the 12 only contributes a little bit. And in order to find expected value, we add all of these up. We add all these contributions up. And we see what's left. And what do you know? Our expected value, or the mu sub x, is 7. So over time, what we'll see is not necessarily over time, but over many, many rolls of the die, what we'll see is, on average, the expected value is 7. That's the mean. That's going to be the mean of this probability distribution. All right. So that's expected value. And so now let's move on to some examples. We have all the tools of the game. All right. So in example 1, at the state fair, you can play Fish for Cash, a game of chance that costs $1 to play. You blindly fish out a card that has a dollar amount that you have won from a giant fishbowl. The game has these probabilities of winning posted on the wall. Is it worth playing this game? So here we see, okay, here are the winnings you could potentially earn. You could win from $1 all the way up to $900, right? And here are your chances of winning. So you have 1 out of 10 chance of earning back your $1, right? But, and you have 1 out of 120,000 of winning $900, right? So getting a lot of bang for your buck, right? But is it worth really playing this game? Well, I've put all of this information on the example 1 tab, right? So these are the winnings, and I've just once again I've put them in here, and Excel has changed it into decimal form. Well, the first thing you want to do is check whether all of these probabilities actually add up to 1, right? Because remember, these are just posted on the wall. You don't know if they're telling you the whole story, right? So let's sum these probabilities up, and make sure that we've covered the entire space of winnings and probability of those winnings. These probabilities only cover 22% of that probability space, right? And there's a probability of 1, right? 100% is the total. So let's think. What must be missing? Well, I think the game probably doesn't advertise that you have the probability of winning nothing, right? So there's that probability, and they're probably just not telling you. So let's see. I am going to take all of this and add a row here. And in this row, I'm going to put 0 as the potential winnings, right? And the probability of getting 0 should be, there we go, should be 1 minus the sum of all the rest of the possible outcomes, right? And that's almost 78%. So you have a high likelihood of winning nothing, right? But once we do this, if we add up all of these, including the 0 one now we should have a sum total of 1. And that's good. We want that. Because this shows us this is now a complete probability distribution of the random variable winnings. Okay? All right. So what is the contribution of each of these winnings to this expected value? Over time, or over many, many plays of this game, what is the average winnings, right? Well, let's look at each one's contribution. And then multiply that all out. And then we sum these up. So when we look at the sum here, we see 60 cents is the expected value. Even though, there's this chance of winning $900, that's way more than 60 cents. It turns out that on average, if you play the game over and over and over and over and over, the average winnings is going to be about 60 cents. Well, you can win 60 cents on average, so the expected value of winnings, so maybe I'll put it as W, or, otherwise we could write it as mu of W, right? This is 60 cents. Is it worth playing this game? Well, it does cost you $1 to play the game, right? So if you play the game over and over, let's say you play the game 100 times, right? That's going to cost you $100, right? But over time, if you multiply this by 100, right, you're only going to win $60 for every $100 that you spend, right? So that's not really worth it. Over the long haul, you're going to be losing money. Now, expected value, I should say one thing. It doesn't matter that much if you're just going to play the game once, right? It's not going to tell you whether that card that you pick is going to be 60 cents. Because remember, there's no possible way you could earn 60 cents. So this is not what that means. It's probably very likely to be 0, right? Because that's 79%, right? 4 out of 5 times you're going to be drawing 0, right? So it's not about any one particular turn. And so you might think, oh, that's sort of useless, right? But actually it's not. Flip yourself around and put yourself in the seat of the guy who owns this game, Fish for Cash, right? You want to know the expected value if you're the owner of the game, because you want to know, on average, like all these different people are going to play, are you going to be losing money at the end of the day, or are you going to be raking it in, right? And what the owner of this game would say is, this is a good game, because if people play, even though I will lose 60 cents for every dollar, roughly, on average, I'll be gaining 40 of their cents, right? So that's my profit. So, this isn't really for just single people. Like, we're not trying to predict single events, but we're trying to predict events over time and over many, many examples.